A very warm welcome to all of us joining today as a part of India Space Week 2026 under the theme Space Education and Research. Today, we are going to explore one of the most fascinating and fundamental technologies behind every space mission rockets. From carrying satellites into orbit to enabling deep space exploration, rockets are the powerful vehicles that transform our ambitions beyond Earth. Behind every successful launch lies a combination of physics, engineering, precision, innovation, and most importantly, the spirit of exploration. And to take us deeper into the fascinating world of rockets and propulsion, we are privileged to have with us an accomplished aerospace engineer, entrepreneur, and rocketry innovator, Mr. Advait Sidhana Sir, co-founder of Thrust Tech India. Sir is known for his contributions to hands-on rocketry education and has been organized for his participation in the international CANSAT US competition. He co-founded Thrust Tech India, an aerospace and defense technology venture focused on advancing indigenous rocket systems, UAVs, and practical space education across Indian academic institutions. His technical work spans research in MEMS-based solid propellant microthrusters and Martian resource utilization, along with conducting practical workshops in aerodynamics and propulsion at prestigious institutions including IIT Roorkee, IIT Kanpur, VIT Vellore, UPES Dehradun, and SRM University. Sir has also contributed research papers to reputed platforms including AIAA and IGCA, reflecting his continued involvement in aerospace research and innovation. It is truly a pleasure to have Mr. Advait Sidhana sir with us today, and we look forward to gaining valuable insights into the science, engineering, and innovation that power rockets and shape the future of space exploration. So, without taking any further time, let us begin today's exciting journey into the world of rockets launching the future. So, we are delighted to have you with us. Now, I would like you to kindly take over the session and enlighten our students with your valuable knowledge and expertise. Over to you, sir.
Thank you, ma'am, for the introduction. I'll just share my screen and start the session.
Yes, so please share your screen. Yes, sir, it's visible. Thank you, sir.
Okay. So, hi everyone. Today we will going to start with the basics of the rocket, like what are the different components from structures to propulsion system to aerodynamics. Then we will try to learn a basic software where we can actually design the whole rocket. So just I wanted to start with a brief introduction of rocketry, how our rocket looks like in today's world, how we see them, but how we initiated, how humans initiated with the rocket concept. So let's start with the history, and then we will go to the software, the basic software, which called Open Rocket. It's free software on the Google. You can download it and do it with me also. So let's start with the history of rocketry. Generally, the Chinese people figure out how to make a gunpowder. Okay, so there are three different components in a gunpowder, and there is an oxidizer, there is a fuel, and they burn it to actually celebrate in their festivals as a cracker. At a moment, the cracker failed and it started to propel. There is a cracker and it has a hole in it. So all the flame, which is all the combustion which happened inside the container, it exhale from a point, and that give that object a thrust. And then human came to know that this can be a thing which is useful for us also. So they make these kind of crackers and it an arrow for the war. Okay. Then the same concept went in 17th century to the Europeans, and they actually fixed all these rockets. They installed sort of rockets in a cart so that the cart can be propelled by these kind of rockets. These are still not very good engineering, but in the 20th century, when uh, there is a actual industrial revolution is happening, there is a rocket called V2. It is a German rocket, and it is the first object which is human made went to the space. So this is actually a sort of missile. Germans actually made it. This technology is developed because of the World War II. This rocket is actually liquid, having a liquid propulsion in it. So what is liquid propulsion? What is hybrid? What is solid? We will come to it. But let's understand, actually we are making rockets like this, and suddenly we started to make rocket like these. So right now in our India, there are only two institutions who have the tested liquid engine. The first one is obviously ISRO, and the second one is the recent one, which is Skyroot. Skyroot used initial three stages which are solid, because liquid is bit complex, and the last stage to install a satellite. Generally satellite is installed on the top of the rocket in this section, in this image, in this section. So the first stage will be something like this, the second one here, the third one here, and the fourth one is here. To install a satellite in orbit, you really need to regulate your thrust or your strength of impulse in the space, so that controllability comes with the liquid engine. We will understand it better in the propulsion section. Then once humans can able to make a rocket like these, then they started to increase the size. They start to scale it from V2 to Sputnik or Soyuz. So this is the Russian design. The Sputnik satellite went space with this rocket. You can easily see with the diagram that all these blue attachments are the tankers in which there is a oxygen. The yellow ones are fuel. Then we have the geometry here, which is the engine pipelines, and the red thing is the combustion chamber and the nozzle. On the top there are different stages here also, and here is the satellite Sputnik, the first satellite which went to space. Then we have much we have Soyuz. Then we have one more milestone, which is by the NASA only, which is Saturn V rocket, which actually put our humans to the moon. So that is a great engineering. They used F1 engines in it, five F1 engines on the bottommost stage. Then there is very complex machinery. NASA thought to actually make a station in a low Earth orbit. There are different orbit in the space. The low Earth orbit is just a one orbit, like from the Earth surface. If this is the Earth surface, altitude 0. So from surface sea level to 100 kilometers, there is a common line. Okay, common line. And then we have 200, 300. So from 300 to 900, approx 900 kilometers, we have the orbit called low Earth orbit, or we can say it LEO. Okay, so NASA wanted to set a lab in the space where they can actually do the experiments to understand the vacuum and zero gravity better. So I think you have heard of ISS, International Space Station, ISS. The whole station is built by the Space Shuttle mission. This is very famous spacecraft of USA, the Kalpana Chawla vehicle is the space shuttle itself only. So there are some failures because the complexity of the system is very high. They wanted to make a spacecraft which can carry a huge amount of payload because they have to actually make whole station in a small form in the Earth, and they installed it, they joined it in the space. So they wanted to carry this big structure of the space station. The space station is nearly the size of a football ground. Okay, so you can imagine how big it is. So they actually used to carry the payload. So this is the section of a crew. if you, if you can see this diagram, this is the section of a crew like a pilot in an aircraft. So you can see generally rocket used to be like this is whole propulsion system which is used to lift whole system, whole mass. And at the top you can put a human crew like astronauts, or you can put a satellite payload, any payload. So this is a basic design of a rocket, but because they wanted to actually carry a huge amount of mass into the space, also they wanted to make the system reusable. Okay, so for that, they wanted to make a system which can come to Earth and be able to reuse. So it is not a right term to say reusability. They actually refurbish it. You can't just, as soon as space shuttle come and lands on the Earth, you can't reuse like a aircraft. Just refuel it and you can use it. No, they have to check all the cracks, everything, all the surface, all the electronic system that they are working or not. They actually refurbish it. So they wanted to make it like that. So this is the design which is actually uh, projected, which is there is a rocket tank that this is very famous rocket. You have seen the launch of it. So these are the two boosters. You can see the one booster, second booster. The third tank is the brown one, and the fourth attachment is the aircraft like structure here. So this whole thing is called STS, or a space shuttle mission. So let's understand all the different components, why it is very complex, and how actually this whole system is working. So astronaut used to control whole air spacecraft from the spaceship, which is the spaceship. And you can see the pilot seats like this here. These are the crew section where crew actually have their seats. Whole the section at the bottom, this portion is used for the payload systems. Okay, so you can carry a payload of a huge amount here. Then you have its own thrusters here. You can see the bell nozzle here. So the concept is, when the rocket is on the earth, it needed highest amount of thrust to carry the mass, because at the surface level the gravity is the most. So you wanted a higher amount of thrust to actually counter that gravitational force. So they actually attaches these boosters. You can see the same thing in today's rockets also. There are rockets which actually uses the attachment, the attached rocket, which are called actually the boosters. So boosters are generally in a solid state. They use solid propellant. The booster use solid propellant. Generally you can use liquid. There are some exceptions, like in ISRO itself, there is a rocket called GSLV Mark II, which is having a main stage, the main first stage as solid and the booster stage as a liquid. Okay, but generally we use solid because solid propulsion gives us the advantage of a higher amount of thrust. Okay, at very initial stage. So these are the two boosters of solid propellant. Then we have a tank, brown big tank, this one, this tank. This is actually filled with a liquid propellant. And this whole tank doesn't have any kind of engine in itself. So this is a tank for just storing a propellant, which actually supplies this tank, if you can see the red line, this tank actually supplies its fuel to the ship's rock engine. You can see the yellow two tankers here. So whole propellant comes with the pipeline to the ship and actually ignites here and have thrust. So these are the two different components which actually produces the thrust. The storage tanker is different and the ship is different. So the profile of the launch is somewhat like this is the surface level, and the launch happen. First stage cutoff. First stage cutoff means two boosters go apart like this. Then we only have the middle tanker, the brown color tanker, and this ship together. After reaching the space, they have the detachment of the main cylinder. This ship itself have cold gas thrusters and liquid gas thrusters to actually adjust while reaching the Leo orbit. While reaching the Leo orbit, they have to actually adjust themselves a bit, correction, to actually maintain the orientation of installation of all the components together. So for that, they have like, you can see, if you can able to see, let me erase it. So there are different types of reaction control engines. You can see it here, reaction control engines, and you can see the holes, three hole here, three hole here. So these are the actually the hole of a thruster. So gas comes out from here, and that works like a small engine. And if you want to turn your rocket in this direction, pitch down, actually you can use these thrusters to actually exit all the gases in this upward direction, and you get the reaction force in the downward direction. Similarly, all the sides they have the reaction control thrusters, or we can say reaction control engines like this. So the small engines are few installed in the surface of the spacecraft body to actually correct it, but the primary engines are this booster stage and the liquid stage. Similarly, if you can able to see the black part, if you are able to see this black part, or here on the wings, these are the carbon tiles which is used to actually resist the heat of the atmosphere, because this rocket is not just manufactured to go into the space. It Generally these rockets you are going to have a re-entry. There is a term re-entry which is very difficult, because the amount of heat the rocket produce while re-entering in the earth, because the velocity is more than like Mach 9. Okay, what is Mach 9? Mach 1, you can able to understand the Mach number. Mach number is, if Mach number is 1, if Mach number is 1, that means it is traveling at the speed of sound. Okay. So if the Mach number is 2, it is the twice the speed of a sound. So if I'm saying more than Mach 9, so the whole thing, all the fighter aircraft which we can see today are generally reaches to Mach 2, Mach 2 or Mach 3. You know, there is a missile called BrahMos, which is hypersonic, means it can travel Mach 5 or greater than Mach 5. Okay. Okay. So this spacecraft is actually interacting with the atmospheric air molecules at the speed of more than Mach 9. More than Mach 9. Okay. So generally it creates a huge amount of drag. Now what is drag? Drag is just a name for air friction. Whatever friction which is happening due to the air, that is called the drag. Okay, so drag actually creates, there is a skin friction drag. The peak surface is this, and all the surface like this at the edge, it creates a drag, and which actually increases the temperature. And you can understand the gas which is present in the atmosphere turns into the plasma. So there is a, while the spacecraft re-enters in the Earth, there is a thin layer of plasma around it. So you can understand what is the temperature, how much friction it creates. So that's why they used the carbon tiles to actually resist the temperature and it cannot harm the structure of it. The other thing is the same reason that there is a problem in a group of tile which actually detached while going into the space in the case of Kalpana Chawla's mission. And while coming back to the earth, that patch of the tiles which are actually not stalled, there is a void where the tiles were not present, and that actually creates whole big disaster. And we still remember that disaster. So you can see the actually intensity of that case. They are actually re-entering. They can come to the ground station while the landing site in 5 to 6 minutes, and whole mission failed. A weak mission failed because of just a small failure from the tide. So this is the complexity of space missions. Then we have milestone, which is SpaceX. SpaceX wanted to make a technology which is very affordable. You can do multiple launches if the price of every mission is really less. So that is the mission. So for that, to reduce the cost, the basic answer is to reuse it. So he finds new ways to actually reuse it, like vertical landing of a booster stage, very famous. Then he's actually making a starship which is having the both the upper stage. Starship looks like this, something like this. This is the upper section. It is having a fin, and then the booster stage, sorry, then the booster stage like this. Okay. In the space, this detaches and go to the Mars. Here is Mars, for example. Whole this big stage comes to the point of launching, means the launching pad, and do the vertical landing. And actually, the point is when he actually wants to plan a mission for the Mars, he wanted a sort of one upper section in the space which carries a fuel. It reaches the space, the first stage, the booster stage detached. It went to the space in orbit, and the another ship comes and refuel it in the mid path, and then again it will go finally to the Mars. So this is the larger project, long-term project, which SpaceX is the planning. So which kind of engine actually SpaceX Falcon is using? Raptor engines. Okay, Raptor engines. Okay, they also use Merlin engines in the initial phase, but Raptor engines are the advanced version, which is actually liquid engine, and they uses methane as a propellant. Okay, in the initial days when they are actually making Falcon 1, Falcon 2, and Falcon 9, they use Merlin because it is bit less complex, and that is open system engine. It is not closed system engine. I will explain it what is closed system and what is open system. So this is the basic profile: the launch, the boost stage, then the first stage cutoff. It comes back and it goes into the space. Then there is a futuristic rocket by the NASA. They are planning missions. So you have seen the recent launch of Artemis 2. Artemis 2 is actually the mission which will carry the astronauts into the space. Okay. So They actually took design from two different previous rockets of NASA. The first one is Apollo mission, which is Saturn 5, and the second one is STS, the space shuttle. So you can see there are the boosters, similar like space shuttles. You can see booster 1, booster 2. They are solid propellant. They came from the STS mission, and the middle structure you can see it is like the structure almost depicts the Saturn 5 rocket, but the profile is totally different. The thrust profile, because they are using different engine here. They are using the liquid stage here. So booster stage, the first stage, and the second stage, and then the another stage to correct themselves, the orientation, the attitude control, then the crew. This is the launch abort system. If while launching at the initial stage some mishap happens at the initial stage in the atmosphere, the whole rocket will detach from here, because this is the crew module where the humans are actually seated. So this is the crew module. This cuts from the here, and this rocket actually lift whole portion and go just in the upward direction, because they wanted to make distance from the whole system, because it can blast. That is just a explosive. It is filled with the fuel, and have a safe uh, touchdown with the parachute. Okay, so they did the, you can see on the YouTube, they did this experiment just 1 year before this launch abort system test. Similarly, we also the NASA and sorry, the ISRO and India is also planning to actually launch humans by their own rockets. So they also tested last year the same system, launch abort system. There is a video. You can see it. They actually attached the whole crew module and the abort system on a booster stage of GSLV, and they tested it. Now let's understand few rocket technology of India. So the purpose of India is not to make a very heavy lifting rockets, but to make a rocket which are not which are very cost effective, and which can carry medium mass payloads into the low Earth orbit, or geo orbit, or polar orbit. So here are different rockets. Like this was the first rocket, satellite launch vehicle. Whole rocket was having a solid propulsion system, then augmented. Then we have one more, which is this is SLV. This is ASLV. Then we have one more, which is SLV3. Okay, so there are four different stages of solid. One, two, three, four, and the payload here. And the payload. All the stages are solid propellant based. Then we have the PSLV. The ISRO is using PSLV. Like the last mission of the ISRO is PSLV only, which is not 100% successful. From the last two flights of the ISRO PSLV, there are some error. But what I trying to explain is there is a PSLV rocket which actually used India used liquid engines uh, in PSLV in their 90s, from 1995. The famous engine called Vikas engine, they actually use the liquid engine here, and we are able to from 1995 we have the capability to actually install the commercial and the government satellites into the space. We can actually install the whole satellite system into the specific orbit. We can do orbit insertions. We can do attitude control. I'm not talking about altitude control. Altitude control is the wrong term. I'm saying attitude control. What is attitude control? So in space, you are having like 6 degree of freedom in space. If this is my satellite, if this is my CubeSat, this satellite can roll like this or turn like this, okay, or it can move in linear motion in 3 dimensions, x, y, and z. So to actually roll it or rotate it or giving the linear motion, this is called the attitude control. Attitude control. For that, we actually uses thrusters. The same thing which I told you in the STS system, the small here, the small holes, correct? These small holes, reaction control engines. This is the term is actually attitude control. So you can do the attitude control with the liquid engines in the space. Okay. Then we have the upgraded version. This is PSLV, which is used to actually install the satellite in the polar orbit. If this is my Earth, if this is my Earth, here is the North Pole, here is the South Pole. So if I wanted to install my satellite, which will be in the orbit of like which will be in polar orbit, like which will r- revolve in the north to south, which will rotate in the north to south. Okay, like this, in this direction or this direction. Then I will use the PSLV rocket. For higher altitude, like from 30,000 kilometers from Earth, 30,000 to more, like 50 or 60,000, that is called geostationary orbit. Okay, so we use GSLV. You can see PSLV, Polar Satellite Launch Vehicle, GSLV, Geosynchronous or Geostationary Satellite Launch Vehicle. So we have two, GSLV Mark II, this one is Mark II, this one is Mark III. Now I told you about, like just in a few previous slide, I told you about that generally the booster stage is solid and the uh, there are some exceptions which actually using the liquid stage as a booster stage. So in this augmented satellite launch vehicle, there are the uh, booster stage, which is 1 and 2, solid. This is the booster stage. They have different type of booster stage, like they have the versions like XL, DL, and SL sort of versions. The XL actually includes the maximum amount of thrusters. DL have the much lesser amount of thrusters, and SL is the smallest one. They use the small thrusters around the PSLV. Similarly, in Mark II, GSLV Mark II, we have the boosters here. And actually, these boosters are not solid based, solid propellant based. These are the liquid. And the main engine here, the main beam of the structure like this, the main engine is of solid state. Then we come to the Mark III, which is also called LVM3. LVM3. So this is a new name. The same rocket is used for Chandrayaan 2, Chandrayaan 3. You can see there are two boosters which are called S200, S200 boosters. These are the solid fuel boosters. Then we have a liquid stage here, and then we have the semi-cryogenic or cryogenic stage here. So we are having L110 engine here, S200 as booster, and C25 as a cryogenic or semi-cryogenic engine. So cryogenic engines are also a type of liquid engine only. We will cover it in a propulsion system. So let's understand what are the different components in the PSLV. I think I already explained in this uh, series of rockets diagram only. So uh, let's understand these are the solid stages. Then there are alternate stages like stage one is of solid, stage two is of liquid, stage three is of solid, and stage four is of liquid. So there are four stages apart from the booster stage. So the first is solid, liquid, like this. In the So you can see what kind of solid propellant actually PSLV is using on in stage one. That is solid HTPV. HTPV is a fuel. Okay. Then on the second stage, N2O4 is an oxidizer. UDMH is a fuel. Again, in the third stage, they are using same as stage one. And at the last stage, they are using monomethyl hydrazine. Okay. So it is a fuel and the oxidizer. Then we have GSLV. So again, you can understand this is the GSLV. They are using liquid boosters here. You can find the same diagram if you wanted to actually find out what are the dimensions of the rocket and everything on the Google. Similarly, GSLV Mark 3, this is Mark 3. They are using HTBV solid stage for the boosters, liquid, same as PSLV. And the third one is you can see C25 cryo stage. The cryo stages, they store their oxidizer and propellant in a minus temperature, in very cold temperature. Like oxygen is stored nearly to minus 183 degrees Celsius. And here we are using liquid oxygen and liquid hydrogen. Hydrogen generally remains in minus 200, approximately minus 200 degrees Celsius. So these are really cold temperatures, and it is very hard to store the liquid, all different two chemicals in this uh, cool temperature. So the storage is very difficult, and uh, the you have to pump the oxidizer and fuel into the combustion chamber to actually have a good mixing and good combustion uh, to get a good output as a force. So that's why it is very complex stage. The cryogenic is very complex stage to actually store uh, fuel and oxidizer, that also to actually burn it in very efficient manner. So it is a type of a liquid engine only. Now let's understand what actually we are making is like my startup is Thrust Tech India, and we are into high power rockets. Okay, so you understand in general when you imagine rockets, what are the rockets? You generally imagine about launch vehicles. All the rockets which I generally um, like displayed you here in the slides are from NASA rockets to Roscosmos. Roscosmos is the agency of Russia. To the ISRO's rocket. Those are the launch vehicles. They actually go nearly to 300 kilometers till 50,000 kilometers. Okay. And few rockets actually go to the moon also. So those rockets are called launch vehicles. If you want to start rocketry by your own, you have to make a model rocket. Then you can go to the sounding rocket. So the sounding rocket and model rockets comes under the experimental rocket. Okay, it comes under these experimental rockets. So these are the rockets where you try to understand the flight path, what is the aerodynamics in the model rockets. In the model rockets, you try to understand a basic structure of rocket. What is the application if this is my rocket? If this is my rocket, these are our sounding rocket, and this is our model rocket. Okay, first people start with the model rocket if they wanted to understand the rocketry. This is the nose cone. This is the nose cone. This is the body tube. This is the fin. So what is the actual function of all these components? Then we have the propulsion device inside it, inside the body tube. If you wanted to put some payload, you can put it here. Like if you want to make a Arduino system, a basic Arduino system to find the altitude, just add code in the Arduino Nano, attach it with the BMP sensor, which is barometric sensor. BMP, this is flight controller connected with the battery. Okay. So this is the basic system you can put here for the model rockets. So in model rockets, you understand how to design, what kind of design you actually want in the rocket. This is not the conical nose cone is like this, the sharp one. You can see the black nose cone here is bit curved. It is like this. Sorry, I drawing this not good. Okay, there are elliptical nose cones like this, but this one is bit sharp. This is ogive shape. This kind of shape. Or what should be the length of the body tube? How much should be the diameter of it? How should we actually design the fins? These are the actual questions. Okay. So we actually understand all this thing with the small systems like model rockets. When we actually understand how, if I'm designing the specific component of this dimension, this will be the result. Then you go to the sounding rockets, which can go few kilometers. Okay, because this is very affordable. The model rockets are affordable. You can understand, you can learn with lower cost. But when you have all the calculations, you can go to the sounding rocket and actually do some good experiment in the atmosphere. You can put a can set here, a can shaped satellite, or you can use a CubeSat here, 1 unit CubeSat. So there is a terminology in CubeSat which is, if I am saying 1 U CubeSat, that means the cube, there is a cube which is having breadth of 10 centimeters, height of 10 centimeters, and length of 10 centimeters. If I'm using 2U, that means it become cuboid, not cube, like this. So now I'm having 2 dimension 10 only, and the length will be, or the height will be 20. So that will be called 2U. Then similarly 3U, 4U, you can attach the blocks. Okay. So you can actually install these kind of precise satellite system, or you should say, if it is not going in the space, you can say it as a payload, precise payload system into the sounding rockets. So I will just explain you about what is the structure part, why structure, how the structure works, what are the materials we can use, the basic aerodynamics, then we have the parachute, deployment mechanism, propulsion system, and nozzle. So there are different kinds of loads, okay, like axial load. Axial loadings are, if this is my rocket, if this is my rocket, if this is my rocket, this is the longitudinal axis, correct? This line is the longitudinal axis. All the forces which are actually applying in outward direction, like which is actually stretching the rocket in upwards and downwards, or they are actually compressing it. All the forces which are in the direction of the longitudinal axis is called the axial force. Okay, so the compress and the tension. So these are the forces which generally applies on the rocket. Then we have the shear forces, like at this point, at this point of the rocket, the forces in this direction, and at this point, the forces in this direction. Okay, these kind of forces actually applies on the rocket. For that, we have to find out what will be the suitable material. Like we have the material of model rocket. Okay, we have the model rocket. Then we have the sounding rocket. Sounding rocket actually experience much higher amount of load than the model rockets. Model rockets generally go from 50 meters to, you can say, 500 meters. Okay, so this can be made by the cardboard. The body tube can be made of cardboard tube. There is a wood called balsa wood. It is like a foam, very lightweight wood and very easy to craft. So you can actually craft a whole body structure or the fin structure by it. Okay. Then we have the PVC, the similar kind of pipe we see for our water supply in our homes. Then we have the 3D printed parts, plastic parts, like you can use PLA or ABS or PETG. And then we have, if your rocket is going at very high, your model rocket is having a good velocity, you can use composite materials also. What are the composite materials? The composite materials are actually the materials which are having two components. The first component is reinforcement, okay, and the second component is the binder. So anything which is having these two components, like carbon fiber composite, there is a fabric which is made up of weaved threads. Okay, fabric is made up of threads. So if this is the mesh of a fabric, there are different thread there are different threads which are weaved together. And if I pour some resin on it and cure it, it will become a solid plate like structure or sheet, solid sheet. Okay. So this is the basic concept of composite materials. You can use carbon fiber composite or glass fiber composite, or you can use Kevlar. This is the Kevlar material I have written here. It can be used as a composite material. For example, the wood in the trees is also composite, and your bone is also composite material. So that's how we actually use. What is the application of composite material? If you want a very lightweight material having a very high strength, so you can go for the composite material. If your budget is limited, you should choose glass fiber rather than the carbon fiber. So we have different kind of composite in the market. You can use anything. Then we have the aluminium alloy. Same thing I'm saying. If you want a good strength with a lightweight, so aluminium is also a nice option to select. Steel alloy. If you can, if you really need higher strength and it is like a necessity, you can use steel in some part, like in the engine. The temperatures are really high, so you can use steel in it. The titanium, you can use titanium if temperature is reaching more than 1000 or 1200 degrees Celsius for large amount of duration, like for 20 seconds or 15 seconds. Okay, so in rockets, the general burnout time for the sounding or a model rocket, which are generally planned to go for 1 kilometer to 3 kilometers, the burn time is nearly 3 seconds, 3 seconds to 6 seconds. That's it. And if you are having burn of like 12 seconds or 15 seconds, that means the combustion is continuously happening in the casing for 12 to 15 seconds, and the material have to resist the temperature for 15 seconds. And generally it is not possible in mild steel or in normal steel. So then we use titanium, but there are drawbacks of titanium also. We'll compare all the material in the next slide. Then we have the Kevlar. Kevlar is a very good material, having a very good strength. It is used in a bulletproof jackets. It is used in parachutes, and you can use it as a composite material also. So here is a basic comparison. You can understand the material. Here is the material. Aluminium, we have the aluminium, we have the steel, we have the titanium, and we have the two composite material. Okay. So these are the materials which are not high strength material. So we will just try to see the above materials. Okay. Density means you can understand higher the density, higher the weight. Okay. So you can see the density is the highest, 7.9. Okay, titanium is lightweighted, aluminum is light, and the composites are lighter than the aluminum itself. Then we have the strength. The tensile strength is the stretch outwards, compressive inwards. Okay, so these two things, these two categories are to just understand the strength comparison. Then the thermal resistance and the cost. Cost is very important when you actually engineer anything. You can't neglect the category of cost. So aluminum is used when you don't need a very high thermal resistive thing. A moderate strength is fine for you, and you want really lightweight things. So aluminum is the perfect option. But if the thermal resistance and the tensile and compressive strength is very high, and you wanted a material which can sustain the thermal loads as well as the tension and compressive loads, and you have no issues with the weight for this specific component, you can go with the stainless steel or mild steel. MS, we say it as MS, stainless steel as SS, and there is HS, hardened steel. Okay, you can select any kind of material from it. There is a difference of carbon content in all of them. Okay, so SS is really hard, MS is bit softer, HS is also really hard. Then we have titanium. Titanium is one of the best material. Okay, because it gives you lightweight, good strength, and very good uh, thermal resistive strength. But the only drawback is the extremely high cost. It is very costly. Also, the machining of the material is really high. Like, it is really hard material, so that if you wanted to machine it, if you wanted to make a cube of titanium turn into the sphere, okay, so you will do CNC. The cost of machining the CNC is really high because it is not easy to machine it. It is not easy to cut it. Then we have the composite material. Now we wanted a very huge amount of strength. Okay, so the aluminum is not in the option. We wanted a very high amount of uh, thermal resistance. Okay, so aluminum is not there. We want a very light material, and we want a strength like titanium, and we want a cost in a moderate way. So we use fiberglass or carbon fiber composite. So generally, all the student teams or all the students or all the amateur rocketeers who are making a sounding rocket, they generally use fiberglass. In the advanced version, they can move to the carbon fiber composites. So we actually understood what is all about the material part. Then let's understand what is aerodynamics. What is aerodynamics? So in the rocket, if this is the rocket, this is the upper section, this is the nose cone. These are the fins. So basically, four type of forces are acting on the rocket body. The four forces are thrust, thrust, drag, then we have lift, then we have gravity or weight. Okay, so these are the four forces which are applying on any object which is flying in the atmosphere. To understand all these forces better, we should look to the aircraft. So if this is the aircraft side profile, this is the side view. So engine is actually here, which is releasing all the exhaust gases in this direction. From the Newton's law, we are getting the reaction force in forward direction. So that's how we are getting the thrust. And the thrust uh, direction is always in the forward direction where you are heading. Okay, so we understood thrust. Then we have the drag. So drag comes with the thrust and lift. Okay, so drag is, I just told you that drag is the friction from air, the friction from the air. So if you are, the aircraft is moving in an atmosphere and it is continuously interacting with the air molecules. Okay, so whatever force which is actually resisting it, when you take your palm out from the car's window, you can feel the resistance. That resistance is called drag. So that drag direction is always opposite to the thrust, always opposite to the thrust. So if this is the direction of thrust, this is thrust, this will be the drag. Then we have the lift. Then we have the lift. What is lift? Lift is the lift is in upward direction. Lift is always perpendicular. Lift is always perpendicular to the thrust. And then we have the gravity or weight, which is always pointing towards the Earth's center. So now we understand four forces and their direction. The thrust will be always forward. Drag will be opposite to thrust. Lift will be perpendicular to the thrust, and the gravity will be downwards. Let's understand what is lift. Okay, so in aircraft, if this is my aircraft, this is my aircraft, and if I generally my wing is generating the lift, the generation of lift is done by the wings. Okay, so if I cut this wing, if I cut this wing, and I see this part, the cross section part, we say it as a cross section. If I cut this wing, so I will not see a flat plate like this. The wing is not like rectangular plate if I cut it from between. Okay, this is not the cross section. The wing will look like this, a leaf like structure. Okay, and this is called the airfoil. Wing is like this. If I'm cutting the wing like this, I will see a airfoil. This is called the airfoil. Okay, the shape is called airfoil, and the majority of aerodynamics is depend on the airfoil. If you see, if you fly drones, this is the top view of drone. One arm, second arm, third arm, and fourth arm. We have the motors here, four motors of quadcopter, and there are propellers on it. Okay, four propellers like in drone. These propellers, if I cut these propellers, now from here, from here, from here, from here, and you see the cross section, you will see different airfoil shapes. If I see this one, if I cut it from the top and see it, it will be look like this. If I cut it from the middle part, it will look like something like this, very thin shape. And if I look from the junction of the motor, it will look like a very small part like this. So we are having three different geometries, one geometry, second geometry, and the third geometry of airfoil only. So this shape is called airfoil, which is used to generate lift. Okay. So there are two basic concept of lift, how lift is generated. Lift is the upward force. Okay. The first is, if this is my airfoil, okay, this is my airfoil, and it is moving in this direction. So all the air stream, we call it, we see the air in the stream form, like line form, is going from above and from the below of the shape. Okay, this geometry or this shape is allowing this whole air stream to have a velocity difference. So the air stream which is moving above the airfoil here, it is having a higher velocity. Velocity is higher because of the geometry, and the air which is moving from the bottom of the geometry, it is having less velocity compared to the above airstream. So this change in velocity through the Bernoulli's equation or through the Bernoulli's theorem, higher the speed, if velocity is high, pressure will be low, and if velocity is less, pressure will be high. Sorry, pressure. So high velocity, low pressure, low velocity, high pressure. So we are having high velocity on the top because of the geometry. That's why we are actually making a region which is a low pressure region. Low pressure. And comparatively, the stream which is moving here, it is having a high pressure. High pressure. So all the air which is in the bottom of the geometry will push this structure because they wanted to actually go in the above section. Correct? Because here is low. Always pressure goes from low to high. That's how we get the upward force, and that is the lift. Okay, this is the first concept. Similarly, we are having the shape of airfoil also do one more thing. This is the airfoil shape. Again, moving in this direction. All the air is coming in this direction. And the air will just slide because of the geometry on the surface. And there is no separation point. The separation point is when if my air will come like this and go like this, it will not follow the structure, the shape of the airfoil. It will just go apart. This is called the separation point. At this point, the lift reduces. Lift doesn't generate. If it is actually because there is a property of air that cause like there is a property of water of surface tension. They actually the molecule sticks to each other. It's a property. Similarly, there is a Wanda effect. Wanda effect. We say it Wanda effect, which tells us there is a tendency of air to stick to the object. They actually try to stick to the object as much as possible. That's how air follows the shape of airfoil. Okay. So you can see this geometry actually guided the horizontal airs in the downward direction. Here, at this point, the direction of air is horizontal. At this point, this is point A, this is point B. The air direction is in downwards direction. You can see this downwash is actually giving us the reaction force in upward direction. This is all the reason of lift. That's how we are getting lift. You know how we are getting thrust. Okay. Okay. Now let's understand very quickly what is the propulsion system. Okay. We have solid propulsion system. We have liquid propulsion system, and we have hybrid. We also have electrical propulsion system, which generally use in the space, like ion thruster or hall thrusters or resistor jet, things like that. But these are the basic three chemical propulsion systems. Okay, three chemical propulsion systems. So the first one is if you want to burn anything, you need three different components. Like the first one is oxygen, the second thing is fuel, the third one is heat. So if you want to burn a wood, the oxygen will be in the atmosphere. The air is the oxygen, fuel is the wood, heat, you will give the heat. You will actually give the heat by the match or by the lighter, anyhow. So similarly, these solid and liquid term is defined that if you want to burn the propellant is the mix of oxidizer and fuel. Okay, these two components, oxidizer and fuel. So oxidizer is should be in the solid form, and fuel should be also in the solid form. Now, some people can confuse that we know fuel like kerosene, like petrol. How can it be in a solid form? So, have you seen gunpowder in Diwali? All the crackers, you can see the powder, the black powder or the powder. Okay, that is having a powdered form of oxygen in it. Okay, powdered form of fuel in it, like charcoal, and one more additive they have for the cat as a catalyst to increase the burn, and you actually ignite it and it burns. If you actually isolate a box, that there is a vacuum in the box. Okay, there is a vacuum in the box, and if you put a black powder in it, it can burn. I'm just saying it doesn't need a atmospheric oxygen to burn because it have its own oxygen in the powdered form. Similarly, there are the powdered oxidizer and fuel for the solid propulsion also. Okay, then we have the liquid. You can easily imagine the oxygen and fuel is in liquid form. Okay, and then we have a hybrid. We can have a section in which we are having a solid fuel. We are having a solid fuel like this, and actually we are supplying a liquid oxygen to it. So the O2 is liquid, still liquid, but the fuel is solid. So this will be a hybrid. Why we did this? Why we actually make hybrid? Sorry, hybrid. We how Why we actually go to the hybrid? Because we wanted to take advantage of solids and advantage of liquids. Okay, so we wanted to make a less complex system like solid is very less complex. Liquid is very high complex, so we wanted a less complex thing, but having a controllability. Like solid, this black powder is an example of solid propellant, correct? So when you actually fly Diwali rockets, okay, this is just an example. Don't ever compare the model rockets with the Diwali rockets, because Diwali rockets are uncalculative rockets, but model rocket you actually calculate how much altitude it should reach. Okay, so this is the black powder, which is, when you actually starts to burn it, it will not stop. You can't control it. It will only stop when it is finished. The whole burnout will happen. Then only the burning will stop. But in liquid, there is an example of liquid like your kitchen stove. You are having a LPG gas cylinder. This is the cylinder. There is a pipeline and there is a stove. Okay, and you have a regulator here. So this liquid you can control. You can easily control it by the knob, that how much intensity you need for the burn. Same thing happens in liquid engines also. You can actually control it. So by making a hybrid engine, they can have the less complex thing as a fuel mold, stack of fuel, and you can supply a liquid oxygen, and you can control it. You can just control liquid oxygen by your hand. So as soon as you stop supplying liquid oxygen, it will stop burning, because we need three things to burn. Okay. So solid is less complex, high thrust, but less efficient. Okay. Liquid is complex, good thrust, but very efficient. Very efficient. Very efficient. Why? Now you can say what is high thrust but less efficient and what is good thrust but very efficient. Solid, there is a term called specific impulse. We say it ISP. Means ISP is for specific, I is for impulse. Is like total force by per unit, per unit propellant. Okay. So when you drive your car in the first gear, you get a maximum amount of torque. It is like a solid. That is solid fuel. That's why we have the booster stage in solid. So the first gear actually requires the highest amount of fuel and it reduces your mileage. So that is the solid stage. High thrust but less efficiency. Okay. And then we have the liquid. It is like third or fourth gear in which you will not get very high amount of thrust like solids, but having a good thrust and good efficiency, having a good mileage. But mileage is very wrong word for the rocket, but for just an explanation, just to explain you, I'm giving you an example of mileage. We said ISP. ISP depends on the propellant as well as the engine. Okay. ISP depends on the propellant and the engine. Okay. So we understand the solid, liquid, and hybrid also. Now we will just try to make one simple rocket on the software, which is called the Open Rocket software. It is very easy software. You can actually design your own model rocket on it. So let's go to the software. So this is the basic UI of a software. Now we wanted to make a rocket which will be having a nose cone, like a sharp top. Then we have a long tube-like structure, which is body tube. Then we have a fin, a small wings on the bottom. Those are called fins. Okay. So let's understand. You can see this is the user interface where you can first check that in the edits, in the preferences, check all the units are in the same like Okay, we are having rocket dimensions and motor dimensions in So we are actually designing our rocket and we are simulating it. We are going to simulate. So we will make very basic rocket in it. You can see here is the rocket design. So when you wanted to actually attach all the structure of the rocket, you will select the rocket design and you can see all the components here. Correct? Then we have the motor configuration where you can actually fit the motor. We are using a motor word. This is not a DC motor, okay, or not a BLDC motor. This is actually an engine. We call it in solid propulsion system. We say motor, not engine. In rocketry terms, try to understand this terminology. In rocketry terms, if you are having any propulsion system, let's come back. I just wanted to explain you one thing. In rocketry terms, what is motor and what is engine? Those engines which are not having any moving part in them are called motors. All the solid engines, solid propellant engines are called motor, and all the liquid engines are called liquid engines. So when you are saying liquid engine, automatically it is liquid propellant. And when you are saying we are using motor in a rocket, so let's understand how engine is not having any moving part. For example, this is my cylindrical casing. This is my cylindrical casing, and I actually uh, uh, put all the fuel inside the casing. This is my propellant filled, correct? Okay. Then I have the nozzle, converging, diverging nozzle. This section is converging, this section is diverging. We say it's CD nozzle. Okay. So in this nozzle, you just wanted to ignite this propellant which is inside the casing, and all the combustion happen inside this chamber. And because they have only one hole in this direction, all the gases will go in outward direction at very high velocity, and we will get the force and counter direction, and we move in this direction. This is the motor, because you are not, there is no moving part inside it, correct? Similarly, what are liquid engines? We are having one tank, we have another tank, we have pipelines. Very basic, we have turbo pump here. Okay, so this is fuel, this is oxygen, we have turbo pump TP. Then that it is actually compressing all the fluid, very high pressure. Okay, and this is going into the combustion chamber to burn. And then we have the nozzle. For this, we are having turbo machinery came here, which is like turbine. There are blades, different blades, which actually rotates to compress the fluid and make a high pressure. Because when it is burning inside the chamber, whenever it burns, it is like a small explosive only, very controlled explosive. Okay, it is burning very fast, so the pressure in the combustion chamber is really high, the pressure is high. So if you wanted to inject the fuel and oxygen inside the chamber, the pressure of the injectors, which are actually injecting the sections here, which are actually injecting all the oxygen, liquid oxygen, and all the fuel inside the chamber, the pressure should be higher here. Then only the high pressure can go into the low pressure. So that's why we wanted very high pressure to be generated in the pipe, in this pipeline. And that happens with the help of turbo pump. Turbo pump is a machine which is actually moving. That is a moving part. The second thing is there is injector. We have different kind of injectors like pintle, shower head, or impinging. Those are the different injector design. These actually supply high pressure fuel and oxygen to the chamber like this. One spray of fuel, then one spray of oxygen. They meet together and they turns into the different particles that we call it as a atomization. Okay, it's a atomization, and mixing is happening and it burns. Okay, so that's why liquid is having a moving part like injectors. There are some injectors which actually moves, and turbo pumps. Or you can, if you are not using turbo pumps, it's a complex machinery, you can use piston system here. Piston system to actually make a pressure inside these tankers. This piston is also moving part, so it still comes under liquid engine, we term it as engine. And what is motor? Having a fuel but not a moving part inside the propulsion device. Back to the software. If you wanted to choose any motor, you will come to the motor and configurations software. When you make whole rocket, then you can come to the flight simulations. Let's make a normal rocket. So all these sections are blurred. You can't select these because we want to actually select the primary structure of the rocket like body or nose cone. And all the other component will fit inside the nose cone or on the body tube. So we will first choose the body tube. Okay, this is the body tube. You can see here are the specifications like what should be the length of the body tube, are all the dimensions are in mm. Okay, so let's put what generally we used to give different types of workshops, basic rocketry workshops. We uses like 51 centimeter or 510 length, 55 as dia, outer diameter. It's a hollow pipe, and the inner diameter is 50. So we get 2.5 as wall thickness here. Then we will override the mass. So we are using our own material. You can select material itself here, but if you wanted to if you want the actual stability of your material, you can use a density criteria. You gave the dimensions and you give the mass, which is the mass of your component, actual component, which is your own design. So the mass will be 129 grams. So now we know the density. Okay, so we already have the body tube. Now select a nose cone. Okay, these are the commercial nose cones. So America have a commercial market, which is actually they actually give the all the rocket components, small rocket components on they are listed on the site. Similarly, we are making the similar kind of ecosystem in India. We are the company which are giving all the sounding and model rocket components on our site. Okay, you can visit to our website, Thrust Tech India. So whatever you are seeing here, okay, so these are the commercial nose cone of US market. Okay, which is actually available in the US market. So you can directly select it. But in India, we have our own dimensions. So we'll close it. And by mistake, I have selected two nose cones. Just delete one. Okay. Now give the dimension to the nose cone. I used ogai shape. Okay. The length of the nose cone will be 12 centimeters or 120. The base diameter will be equal to the body tube itself to actually have a good structure. Okay. So it is 55. Then we have the shoulder. What is shoulder? Just I will put the values in diameter, length, and thickness. See this area of the nose cone. You will understand what is shoulder. I actually wanted to fit this nose cone inside the body tube. So there should be some extended area in the nose cone that will go inside the body tube. So that I am making. That is called shoulder. Okay. So the shoulder will be diameter will be 5. Okay, because we wanted to put inside the body tube, so it should be equal to the ID, inner diameter. The length will be, it is 5 centimeters. So I will 50 mm. The length will be 1 centimeter or 10 mm. So you can see as soon as I do the OK, you can see here there will be excluded part. Correct. Now I will just shift it in a move up direction. So this part is actually inserted in the body tube. That's how it remained intact. Okay. Then we are having different components, like we wanted to stabilize a rocket. So you can see here stability part, which is minus 4.84. For the specific design, it is good to have a stability more than one. Your rocket is stable theoretically if your stability is more than 1. Here we can see minus 4.8, which is near to minus 5. The stability is very, 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 very bad. Okay, it is not good at, it is not at all good. So you wanted this minus 4.8 to be more than 1 to stabilize theoretically. In practical ways, in practical world, if you want to stabilize your model rocket to have a safe and good straight flight, it should be more than 1.5. Okay, near to 1.8. Okay, if you go further than 2, it will be over stabilized, and there is a problem, which is over stabilization is a problem. it will start to like wind caulking will start, over correction will start. So that is also a problem. So the range which we wanted is 1.5 to 1.8. Now how will we actually do it? This red point is CP, and this logo like BMW, the blue one, is CG, center of gravity and center of pressure. So CG is actually where, if there is any object, a point where you can balance the mass of whole object, that is CG. Okay. And the CP is where all the aerodynamic forces balance out at the point. So for example, just try to understand it. There is a, sorry, if you put a rectangular stick out of your window, if this is your car window, and you put your stick outwards and all the air is moving like this, the stick is like this. So let's see it. If my stick is like this, it's actually a bar of a wood. Okay. And all the air is coming in this direction, and it is interacting with him. And actually I want to uh, only hang it with one thread. Okay. And it should be not move in this direction or this direction, it should be stable. So I will find out the surface area of whole thing, and the midpoint will be here, and I will just attach a thread or string with it. So all the air which is actually interacting in this surface is equal to this surface. So all the force will be balanced out. So it will not move in this direction or this direction. So this point will be my CP, center of pressure. So object, all the aerodynamic force is balancing out on that object is called the CP. Okay. The CG is if I wanted to hold at any point. So the mass of this side, this section and this section should be same. Then only I can balance out. So this is the CG, sorry, CG, and this is the CP. These are the 2 points I am talking about. Okay. So when a rocket actually fly, so as soon as I increase the surface area of this section, if this section is bigger, the force of this, understand one thing, it is very simple, that if I increase the surface area of this side of the beam of a wood, beam of the bar, so it will counter more air force, aerodynamic force. So it will move in this direction, because whatever force is generating is in this direction is will be lesser than this direction. So it will move in this direction. So that's why we wanted to make a fin here. This fin structure is used to actually shift our CP. This is the CP point. To balance it out again, I will actually make a new CP point here. And then you can actually see the surface area of this side, and this side is similar. And I can tie it from here, and then it will not move in this direction. So we wanted our CP to shift downward. CP should go down, CG should go up. To make our CG in upward direction, we put all the extra mass here. We are adding mass so that our CG point, which will be here somewhere, it will go up. And to and our CP point is also somewhere here. We wanted to put surface area. We wanted to increase the surface area so that CP will go downwards. Okay. So what will happen if this is my CP, this is my CP, and this is my CG, CG, CP. If the gust of wind come, my rocket is flying in upward direction, and there is a gust of wind, and my rocket is tilted. My rocket will tilt from the axis of CG. Correct. So my rocket will look like this. From the CG point, it will turn. Okay. And here is CP. Now the concept of the total force balancing out, aerodynamic force balancing out will come, because this is the axis where it turned. Now all the aerodynamic force will apply on the CP only, because continuously this force is applying on CP. So that's how all the force will go to the CP, and it will correct it again in initial orientation. So it comes straight. That's why we wanted CG and CP. CG should always be on the top and CP should always be on the bottom. So in here you can see there is something else. You can see red point is CP, which is on the top, and the blue point is should be on the top, but it is on the bottom part. So what can we do? We should increase the surface area at the bottom to actually make it to position it downwards and increase the weight on the top. So if I can just, this is the use of fin to actually stabilize. So the basic is to just increase the stability more than one, positive one. This is minus 4 point something. So let's go to the fin, trapezoidal fin. Okay, select body tube because we wanted to attach the fins on the body tube. Then you can avail the trapezoidal fins. Now we wanted 4 fins, not 3 fins. So we'll 4. Then we have different dimension of fin. Root chord is root. So the surface of the fin which is attached from the body tube, that root line, that is called root chord. If I from 50 I will do 100, this line will increase. This root line will increase. So see, 100. Okay. If I'm doing okay, the line is larger now. Similarly, you can see from minus 4, now I came positive in positive number 0.8, still not 1. So I will just increase the height. I will increase the height. It is 0.9. I will increase the surface area on downward direction. So I'm giving the angle to this whole surface like this. Actually, I am increasing the surface area in the bottom area by giving the angle. So you can see now I am 1.01. I want to make it practically stabilization ke liye, I want to make it more than 1.5. So I can increase the height a bit and increase the angle like this, a bit height, and the tip chord also. Tip chord is this one. This chord is called tip one. This is root, this is tip. Okay, I think this is fine. The fins look fine. Now I can either make fins more larger, or I can either add weight. So I think I should add some weight on the nose cone. So there is dead mass here, mass component. You can say either you can put a payload of 30 grams, or a dead mass also 30 grams. Okay, and we can position it. If I'm So top of the parent component. The parent component is nose cone, and I can select where I have to position it. It is top from the parent component. If I'm doing +1, 2, it will move downwards. Okay, so it should be inside the nose cone. So the position will be somewhere here. Now you can see, as soon as I will do the OK, the stability is 2.17. I just want 1.8, so I can reduce the mass, or I can reduce the surface area of fin. Correct. So let's do 20. Okay. 1.9. Still we have the margin. We can go for the 15 gram. 1.8. Perfect. We wanted 1.8. Here's 1.8. 1.80. Perfect stability, what we wanted. So this is the basic rocket. There are few more components, like if you wanted to attach this rocket on the launch pad, there are launch buttons. If you can see launch buttons, select body tube. Then either you can use launch lugs or launch buttons. rail buttons. Again, commercial tab. So outer diameter is 14 mm. 14 inner is like 7.8 or 8. You can write 8. Then the base height is 0. So you can see a structure here, a button-like structure here. So that will fit inside the rocket. You should there should be two uh, rail buttons. Now they are co-lining with each other. So I will just position it in some other spot. Okay, like this. Now you can see that it is like a T, inverted T. So this T can easily slide on the launch pad rail and it will attach the rocket on this launch pad. Now there is one major component remaining, which is motor, which is propulsion device. The motor will attach on the body tube. Okay. So we'll select the body tube, go to the motor and configuration on the top. Select the body tube here and you can see new configuration. We have a lot of motors here. We generally, for the model rocket, we use E class. Here are A to O class sections. So A class motor is if having, for example, what is A, B, C, D in motors. A class motor is the smallest motor. B will be twice the power of A. C will be twice the power of B. D will be twice the power of C. So we are actually, if we are moving in the alphabets, it is just 2x of the previous letter. Okay. So A is half of the power of B. So we actually calculate this power from total impulse. Total impulse is something we actually calculate the power of motor. I told you about the specific impulse. Similarly, we have the average thrust, total impulse, specific impulse. That's how we actually categorize the motor. For model rocketry, we use E class or F class. So rockets like this can go to up to 150 to 200 meters with the E class motor. Okay. So one thing we have not done till yet, because I have override the mass of the body tube, but not of the nose cone. So it is 27 only, which is very similar. Okay. Then we see if I there was a 28 grams, so I was getting 1.8. Now suddenly the mass is reduced from the top, so the CG point is bit at the bottom side, so it is 1.75. Now you can understand how it actually uh, create the difference. So what is the stability 1.7 caliber? This is just a distance between these 2 points divided by the diameter of the body tube. Okay. Now we will attach the motor, select the new configuration, E class. Okay, so we'll select E16. Okay. So now we have the motor. Now our body tube is having a very large radius. How should we fit it? Then so we are having a ring. We call it centering ring, which actually holds the rocket body tube and rocket motor together. So these are the rings, centering rings. Okay, uh, we can just put the thickness will be 5 mm. The outer diameter will be 50 because the inner diameter of the tube is 50 and we wanted to connect it. Okay, so there are center rings. Override mass 5 grams. duplicated, we wanted 2. Okay, duplicated. And you can see it is at the nose cone. Okay, I think I have not selected the body view. Just delete it and do it once again. I by mistake I selected the nose cone. Select the body tube and then use the centering ring. Yeah. Now 5 mm inner is 30 mm. Okay. Now you can see here is the red line which is centering ring. I wanted to attach 2 centering rings. Okay, with the same dimensions. So what will I do? I will just duplicate it, open one centering ring and shift it like this. So you can see this ring is actually attaching the motor with the body tube. Now we are having very less amount of stability because we attached motor here and motor added extra mass here. Will increase the size of the fins. Okay. And increase the weight here. Like initially I put 30 grams. Let's try and see 30 grams. Yeah, we are having 1.05. We can put 40 grams here. Putting weight will reduce the altitude which this rocket will reach. So you should know the requirement. You wanted to send it as high as possible. So you have to play with the fence itself, with the surface area itself. But if you want a moderate designed rocket, which will go to some specific altitude, you can use a higher thrust motor and increase the weight. Okay. Now it is 2.6. I can do one more thing. Just increase the height a bit. It will be perfect. Sweep angle increase. Yeah, again 1.73. Now you can see a 3D model of it. From side view, we are having a side view 3D figure. So you can see all the components. These are the T slot which will attach on the rail. These are the rings. You can see inside the ring black color motor, 4 fins. Let's see finished, unfinished rocket model like this, and the finished 3D rocket model like this. Cardboard tube, PLA material, 3D printed nose cone, cardboard fins, the motor, everything. Correct. Now let's simulate it. So we are having a design. Go to flight simulations. Okay. Select uh, simulation 2 and you can edit a simulation where all the environment, wind condition and everything, your lat longs, what is the average wind direction, turbulence intensity in the wind, you can find from the Google of your area and you can put the actual values here. Okay. And then you can do the run simulation. Okay. Now let's plot it. You can find we are selecting the altitude, vertical velocity and vertical acceleration. You can do anything like stability, thrust and drag, orientation, anything can plot in the graph. So this is a basic thing. Let's plot it and see. Okay. So because our conditions and the computer input conditions are a bit different. So the blue is altitude. So our rocket, this is the time. So the whole flight was 17-second long. Okay. It reached the apogee to the highest point at the 8 second, and the highest apogee is around more than 290 meters. Okay. Here is the vertical acceleration and everything. So you can actually see it. Other than this plotting, you can see rocket length is this much, diameter is 55 mm, mass with no motor is 2146, Mass with motor is 294. Sorry, 296. Here you can see apogee is 293 meters. Numbers will come. You don't have to plot it again and again. You can see it from here also. So this is the basic rocket design, the basic understanding of model rockets. So I think you understood what is the basic concept of rockets, how you can design your own model rocket and actually do the same. If you are having your own design, you have a body tube of your own, okay, like a shuttlecock box, cylindrical box, and you can actually make a the nose cone is very difficult to make because it is a tensor quantity. It is having curved surface all along, and the cardboard fins you can make or you can buy from our website. We are available. If I will not recommend to make your own motor. It is very dangerous. You should buy from the vendors. uh, we are one of the vendor. So just try to make one. If you can get the correct stability caliber here, 1.73 or 1.8, and you will fly it, and if it will go like what you actually simulated it here, it tells you a lot about the engineering skills you have, how good you can design a basic rocket. So you all should try this. It will ignite a new uh, spark in yourself about the rocketry, and you can actually learn a lot about flight dynamics and flight mechanics of a rocket. That's it from my side. Thank you so much. Uh, I'm glad to share all the knowledge with you all, guys. Thank you.
Thank you so much, sir, for such an insightful and engaging session. Your explanation have given us deeper understanding of the science, engineering, and innovation that go into developing and launching rockets. I'm sure that our participants have gained valuable insights from experience and expertise. So, sir, today we have received several interesting queries from our students through their mails and different platforms. So, we have decided to select a few questions, and I would like to put them forward for you on the behalf of the students.
Sure,
So,
sure,
sir,
ma'am.
shall I begin
Sure,
asking?
sure, sure.
So, first question is that if rocket launches upward, then why do they eventually turn sideways instead of continuing straight up?
So there are two different ways. You are actually talking about the launch vehicles, which we actually see in the television, that they actually turns in some orientation which is horizontal to the earth, because the launch vehicle purpose is not just to go into the space. The actual purpose is to gain a orbit, and the easiest way to arrive till the orbit is to actually use the gravity of the earth. So they don't try to actually go directly into the space in a straight way. They actually take help with the rotation of the earth, the gravitational forces, and they actually insert in the orbit. An orbit is actually rotating around the earth in a horizontal manner only. So the rocket should actually the orbit insertion should happen in that orientation itself. So that's why the launch vehicle tilt at some altitude, and that is controlled, that is actively controlled by a rocket system autonomously. It is feeded in the rocket itself.
Thank you so much, sir, for that answer. Now, moving on to our next question. Why do rockets use multiple stages instead of using one giant fuel tank throughout the journey from launch to orbit?
So it is very basic solution of a problem, that higher the weight you wanted to carry, higher the propellant you will carry. So it is like a loop system in the rocket. If you wanted to carry 5 gram of satellite to the space, it will require, for example, 10 kg fuel. If you want, for that 10 kg fuel, you need extra fuel of 5 kgs. So it is actually for fuel also you wanted extra fuel, because fuel is also a weight. So as soon as you actually divide the portion of the rocket, so that as soon as one stage is over, you cut down the mass, and the whole rocket become lighter, so it can go efficiently in the space. Similarly, there is one more very complex engineering problem, which is called under expansion or over expansion. So as soon as we go into the space, the altitude uh, gives us the low pressure area. Okay, so near to the space, the pressure is really low, and on the surface of Earth, the pressure is really high. So the engine which is actually working on the surface of the Earth will not able to actually perform very efficiently at the high altitude because of the flame distribution from the nozzle. Okay, so that's why we need different engines. For that, we have different stage, and at different stage, we are having different nozzles and engines. Generally, nozzles. So that is the one reason we give different stages, and the main reason is to cut down the weight.
Thank you so much, sir, for that answer. So, next question is that what are some of the major challenges involved in the vertical landing of a rocket?
So the okay, let's see it point by point. SpaceX is doing vertical landing. So first of all, the basic reusability comes with the parachute. It is very easy. You use your stage, and then it will come and touch down to the ocean, or you can soft land it by the parachute itself. The problem in the vertical landing is you have to carry the fuel of returning flight also. So it will take the mass. The second problem is thrust vectoring control. It is a term. You actually, if you wanted to maneuver, if what is the meaning of maneuver, if you wanted to rotate or do any kind of uh, very lame term but acrobatics by the booster, like you wanted to move right or roll it or rotate it anyhow, you will do it by the nozzle itself. Okay, there are some small thruster like space shuttles, but there are main purposes by the nozzle itself. So you move nozzle to actually move whole orientation of the rocket. So that thing is called thrust vector control. So your thrust vector control should be very specific, so that it will align with the surface area and the predicted path, and it will come down. It requires a PID system, a lot of trial and error, a lot of coding, how actually your sensor is giving input to the computer system, and it is actually giving the response to actuator. The actuator is here nozzle, which is actually moving. That is the second problem. And the third problem is itself the stresses, the load stresses. After if you wanted to reuse it, it is already burnt. The stage is burnt, and you do extra factor of safety on the uh, booster stage to reuse it in a well manner. So these are different. There are lot of several issues in the vertical landing, because it can only be happen in liquid engines only, because liquid engines are we can able to control liquid propellant, not the solid propellant. Few hobby rocket people did it with the small rocket, solid rocket motors also, but it is not the right way to do it. So yeah, it can only be happen in the liquid engine only, and these are the problems.
Thank you so much, sir, for that answer. So, the next question that we have is what specific technical skills or projects should a robotics student focus on right now to stand out? And what are the key advice would you give somebody entering in this domain?
Entering in the
Entering in this domain of robotics.
okay, very nice question. So the students who are actually attending this, they can be from different domain. They can be from school. They can choose anything in their future years, or they are currently doing their engineering in some different engineering. So the very simple answer, which actually S. Somnath, the previous ex-ISRO chairman, gave is, we wanted engineers who are system engineers, who can integrate multiple systems together. We don't want engineers which can only give inputs in specific field. So the answer is same. You should know different the working of propulsion as well as the avionics system. to actually work the propulsion system, you should know where to ignite the motor, where you don't have to ignite the motor. For that, you should have the knowledge of bit coding, electronics, and everything. So the answer is, if you are a robotic background student, whole payload domain is open for you. All the rovers which are actually present in the Mars, Perseverance, Curiosity, it comes under robotics itself. You can do that. You can pursue satellites. You can pursue probe. You can make ISS, like ISS thing. The second thing is, try to actually integrate different fields together to make something new. So your own core field is perfect for this domain. Just need an integration so that you can use it. So if you are a CS student, it is higher probability that you will get selected in ISRO than the aerospace engineer. I'm not discouraging aerospace engineers. That is your own field. But yeah, you can use your knowledge in this field anyhow. Yes, ma'am. Next question.
Thank you so much, sir, for that answer. So, our next question is that which application are you using?
Okay, so the software name is Open Rocket. Open, Open, Rocket, Open Rocket. It is a free software on the Google. You can download it and you can try it.
Thank you so much, sir, for that. So, the next question we have is how can geoinformatics student get into this field?
Geoinformatics. Okay, very nice question. So, have you? There are different centers of ISRO in Hyderabad and Dehradun, which is IRS and IRRS. Okay, so whatever data is captured by our satellites, we are actually capturing that data because we wanted to utilize that data on the actual grounds. Okay, so whatever images and all the things, all the map, mineralogical survey, topology, whatever the thing our satellite is seeing, that data comes to these kind of labs, and they actually do the MATLAB simulations in it. They do MATLAB. They have the mathematical model of it. MATLAB is a software. So they actually convert that data to a ground level understandable system. Okay, so everything after the data, we actually receive the data from the satellite. Everything is uh, good for you. All the final implement, like there is water on the soil of moon, you can do this achievement came from the knowledge of geologist and topography, and when we do mineralogical survey around it. So yeah, this is a fine way to do it. You can go to IRS. It's a ISRO thing. You can study there and do the job.
Thank you so much, sir, for that answer. So, now we have just one last question.
Yes, ma'am.
How can a student start research work in space robotics? And where can we find open data sets or simulation tools for research projects?
Okay, so there are two different softwares which are uh, CFD. You can do CFD, computational fluid dynamics, and there is another one which is called FEM. These are actually not the software; these are the techniques to do the simulation. FEM is finite element method. Okay, these two thing can be done in the software called ANSYS. So you can do simulation on the ANSYS, simulation of the loading, simulation of the fluid interaction with these system. The another thing is where you can find the data. If you wanted to start it, the basic version is just gain a knowledge from the YouTube, a very basic knowledge from the YouTube. There are free lectures of MIT, Massachusetts Institute of Technology, on the YouTube. There are whole library, free library. You can understand a basic understanding from there. When you get the basic idea, you can go to the Google Scholar and find out the actual topics in which you wanted to actually research on. Okay, so you can get the actual data. Don't go directly to the research papers from Google Scholar because you will not understand anything. Just first make your foundation from the YouTube lectures and then go to the data set.
Thank you so much, sir, for answering all the questions. So,
Thank
since
you.
we don't have any more questions, do you have anything to say, or shall I conclude with the session now?
Uh, just I want to say, do different kind of experiments, safe experiments. It will give you different kind of knowledge. If you are doing engineering or if you are doing BSc or anything which is non-technical course, if you are studying science, you should do experiments. That's it. Thank you, man.
Thank you so much, sir, for such an insightful and engaging session. On behalf of all the participants, I sincerely thank you for sharing your knowledge and experience with us. I would also like to thank all the participants for their participation and thoughtful questions. With this, we conclude today's session on rockets as a part of India Space Week 2026. Thank you, everybody.